Hey guys, this is James, one of the undergraduate tutors for C100A, and I'm going to be covering a topic that was covered in Professor Korean's lecture number 9 on slide number 17. And it was basically that for a system with a large number of molecules, we can approximate that ln(w) is approximately equal to n ln m over n. So I'll be covering the conditions, why we need these conditions, as well as the derivation formula. So let's talk about the conditions real quick. So the first condition is that m and n must be large. Remember that n refers to the total volume of the system, basically all the positions that the molecules can occupy, and n refers to the specific position / the specific number of molecules we want / are looking at. So when m and n are large, this allows us to use Stirling's approximation, which, if you recall, basically says ln n factorial is approximately equal to n ln n minus n. So that will be important for derivation of this formula. So the second condition is that m must be much larger than n. So this condition allows us to assume that m minus n is approximately equal to m. So with this, we can use these two conditions to actually derivate the formula. So let's go into the actual derivation. So let's recall that w is equal to m factorial over n factorial times m minus n factorial. So knowing this and knowing that we're solving for ln(w), we can essentially break down this formula into sums and differences of natural logs. So we can say that ln(w) is equal to ln m factorial minus ln n factorial minus ln m minus n factorial. So this is where the first condition comes into play. Since we know m and n are both large, this allows us to use Stirling's approximation for all of these terms. So what we're left with now is ln m becomes m ln m minus m. We put a bracket over this. And then the next ln n factorial becomes n ln n minus n. And then the third term becomes a bracket m minus n ln m minus n minus m minus n. So if you look here, we have constant terms here, 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 and here. So we see this is negative m. This becomes, when you distribute it in, this becomes positive, right? And then if you look over here, there's also a negative sign here. So when you distribute this negative sign into here, this becomes positive. So what we're left with is a negative m and a positive m. So these two cancel out, as well as a positive n and a negative n. So these two cancel out as well. So with those canceled out, we're left with this formula, m ln m minus n ln n minus m minus n ln m minus n. So from here we can actually further distribute these two values out and further simplify our equation. So what we're left with is m ln m minus n ln n minus m ln m minus n plus n ln m minus n. So our second condition comes into place here, which is basically we can assume m minus n is approximately equal to m. So this we can say is approximately m as well as this. So what we're left with now is m ln m minus n ln n minus m ln m plus n ln m. So we see here and here, these two terms are the same, but they're just inverse, so we can cancel out. And then these two terms have the same coefficient. It's just different natural logs. So we can actually rewrite this as n ln m over n. Because this is positive and this is negative, remember differences of natural logs is the quotient of the two terms inside. So we see here that we actually are able to derive ln w from this down to this, which is essentially the formula that we have right here. So applications for this come into some problems where they say the volume is very large, such as I believe it was problem set number 6, question number 5, when you were dealing with a large, when it said, if you look back, it said you were dealing with a large system or a large volume, and you also had a large number of molecules. I think it was 1 mole of molecules, so that's 6.022 times 10 to the 23rd. So when they're saying that it's a large system, they're implying that m is large. And when you have 1 mole of molecules, that also implies n is large. So that question wants you to use this approximation. So that's one application I can think of off the top of my head. If you guys have any questions, let me know. Hopefully this video was helpful. All right, thanks for watching, guys.